have been many advances in applying formal methods in industry. And specifically, this has been the case when you look at the hardware industry. So for example, if you look at most modern successful EDA companies, they all have some kind of formal verification offering, such as a formal model checker or other kind of formal verification techniques. When, on the other hand, when you look at software systems, when you look at applying formal verification techniques to large-scale industrial software applications, there have been fewer success stories. There still are some. So there's ComCert, a verified C compiler. There's Cell4, a verified operating system kernel. And there's the HACOM's work where they verified unmanned air vehicle software. So there have been several success stories in applying formal methods to industrial scale software, but usually they are always in the space of safety critical system. Something you don't hear a lot about is somebody formally verifying a web app or some kind of other type of enterprise software. Yet there's like millions, not millions, there's a lot of these pieces of software out there and they impact our life. So why is verifying large-scale enterprise software so hard? Well, there are a couple of reasons. One reason is that because these web applications are usually made out of microservices that communicate over the internet and they're implemented in many different languages, you don't have an accurate architectural model of the thing you're trying to verify. And this makes it very hard to reason about these things. Another issue is economies of scale. Because it doesn't make economical sense to verify something if it's only used once or if it's not used a lot. So what I'm gonna argue here is that actually when you look at this kind of industrial enterprise applications in the cloud, it's actually easier to apply formal methods techniques to them. Not all the challenges will be gone. There still remains plenty of challenges, and I will talk about those later. But there are still, it still becomes a bit more tractable. And going to our first challenge, the accurate architecture model. Well, it turns out that when all of your application is deployed in the cloud, you actually have some computer-readable contract that defines what your application is. You can know what all the compute resources are. And the other advantage is that because they are built on top of the same cloud components, you end up with uniform description languages that you can verify once, and then multiple people can benefit from them. And this is where the idea of economies of scale come from. If you're supporting something a lot of people use, then it pays off to invest in verifying it. Okay, so let's take a deeper look at why verifying a typical, I guess, non-cloud web app is challenging. So let's use as a motivating example this simple photo service web app. So it's a 3-tier application. So here you have, So you have your web tier that has 2 RESTful APIs. You have your login API that processes the login request. You have an upload API that uploads some photos. And in the app tier, you have some authorization service that makes sure your users are authorized. You have a session service that manages state between user interactions, some upload service that actually uploads photos, and finally, some thumbnail service. And then you have your backend data tier, where you have some database for authorization token, authorization credentials, something for another database for user session, and some photo store that actually has the photos. So let's try to prove a property about this application, maybe something very important for security, such as least privilege access. So if you wanted to prove least privilege access about this application, something you'd want to check is that, the authorization service should have access to the authorization database, but none of the other microservices should be able to do that. You may want to prove that the thumbnails service has access to the thumbnail part of the photo store, but not the rest of the database, the rest of the store. And finally, you probably want to show that the web tier cannot access the data tier directly, because this would mean that you're bypassing all authorization, which is obviously not what you want. So in a traditional non-cloud-based application, if you want to prove all of these properties, well, you have to reason about a bunch of things. So one thing is network controls. And those can be implemented in hardware, and sometimes they're also enforced through firewalls, which block packages from certain IP addresses. Then you have to reason about file system permissions. And these control and delegate user access to local data. You have to think about database credentials that control access to the database. You need to think about cryptographic keys that protect the credentials of the database. So the problem here is that it's like a very non-uniform and kind of diverse set of techniques and technologies that all work together to make this application. And checking one property, you have to support all of these different use cases and how they fit together. So, yeah, this is challenging. So let's see what this application would look like if you build it as a web, as a cloud application. Because some of these challenges will become a bit more tractable when you look at the same application in the cloud. Before that, let's do a one-slide overview of what cloud computing is. So the way it works, you have some cloud provider like AWS who provides services such as compute, storage, database, networking, machine learning, all those beautiful things. And what customers do is they use these services as building blocks to build their application logic on top of it. By specifying things like access control configuration, network configuration, or and then combining this API, AWS APIs to get these resources to talk to each other. Of course, now when you're thinking about the security properties of a whole entire cloud application, the correctness of the overall system hinges on the correctness of the underlying building blocks, right? That's a whole different talk that I'm not going to give, which is about verifying the actual microservices in the actual AWS services. So in this talk, I'm going to focus more on the custom application layer. And how do you ensure that if you're assuming that the building blocks you are using are verified, how can you reason about the overall system at this higher level of abstraction? Does this give you any advantages if you want to prove some properties of this? Okay, so now that we've had our introduction to cloud computing, let's see what this simple photo service looks like in the cloud. And ta-da! As you can see, it looks very similar. It's pretty much the same architecture. I just replaced some generic boxes with some nice logos of AWS resources like Lambda and DynamoDB tables and S3. But there is one key difference here. So if you wanna know who can access what, the way that is defined in a cloud application is using an access control policy language. And there are several of these little policies that are associated with different resources or different principles like roles and things like that. And there's a couple of nice things about this. One is they are all in the exact same language. So you have a uniform language for specifying access control in your entire application. The other nice thing about it is because they all live in the cloud, we have a way of collecting all of them. So what you can now do is collect all of everything that defines access control in your application and start building an analyzer that analyzes them and helps you reason about their semantics. So let's see what these access control policies look like. So this is a potential access control policies that you could imagine attaching to the thumbnail service. And this defines what are the actions that this part of this little microservice is allowed to perform. So you have some allow statements and some deny statements. So when you get a request coming in, the request is going to have a principal, that is, who is this request coming from, who's the entity that's going to perform the action. It's going to have an action and a resource that they're performing the action on. And the way this works, we're going to check if there's any allow statement that matches this request. So in this case, we notice there is the first allow statement, matches the action because it's S3 get object, and it also matches the resource. Notice that the resource identifier allows in the allow statement you can use a regular you can use a star so it matches the prefix of it. So great, it matches an allow statement. We grant the request and we deliver the fluffy.jpg image. Let's see what happens if we get a different request. So now we have the same principle, the role thumbnail, and we're also requesting get object, but now it's a different part of the data store we're trying to access. Now we're trying to look in this photo scans, social security number, JPEG image. Well, in this case, we still have the allow statement matching because it's still a prefix of the photos data store path. But it turns out there is also a deny statement in the policy that matches any type of S3 action. And it's, the resources it's targeting are those specifically in the scans directory. So this request will get denied. So the way this works is a request will be allowed if there exists an allow clause that allows it, but there are no deny clauses that deny it. So it turns out, and some of you probably already see this, you can take this policy language and nicely encode it into an SMT formula. So you can define a SMT formula over string variables for the principal, action, and the request that precisely define exactly the request that this policy will allow. So for the first allow statement, you could translate it in a clause that constrains your principal, action, and resource to what the allow statement specifies. We do the same for the other ones, so we keep adding disjunctions here. And finally, for the deny statement, and you add a clause at the end, ensuring that the principal, action, and resource do not match this deny statement. So once you can write an SMT formula that precisely defines all the requests that the policy can allow, now you can start verifying properties about it. You can check what the least privilege access property we had before. And I won't go into details about that because, oh, sorry. I won't go into any details about that because we have a bunch of blog posts and there's a paper from FNCAD 2018 if you want to read it. But this approach has worked very well because, again, because you have a unified language, you can translate into a precise formula, and any kind of technology and automation you build there, everybody who builds on top of it benefits from it. Okay, so this is nice, but let's try to prove another security property for our simple photo cloud service. So say we want to make sure that our application is not vulnerable to cross-site scripting. Cross-site scripting is one of the OWASP top 10 security vulnerabilities. It's basically what happens if, when you're building your web app, you take untrusted data from the network. So in this example, the data is coming from the HTTP servlet request parameter. And then you use that data to build a web page. So in this case, we're just using the writer from the HTTP response to directly write the username in this nice little happy welcome prompt. The problem with doing this is that now you basically, if the malicious user has some cleverly crafted username, something involving scripts and other bits of JavaScript, you basically end up getting remote code execution here. And the way to mitigate this is you need to sanitize your untrusted data. So in this example, we are calling this policy sanitize API, and that's going to sanitize the attacker control data. And now you can print this welcome message very easily. So it turns out if you want to detect issues such as cross-site scripting, you can formulate this problem very naturally in what is known as taint tracking. And what taint tracking does is it tries to answer the following question. Can data flow from a source to a sink without first going through a sanitizer? And in this case, you can see the source of the sink and sanitize corresponding to our problem. Okay, and taint tracking is actually a really important problem for security. It turns out it's not just cross-site scripting. It's a lot of the OWASP top 10 that you can check with taint tracking. And just in general, from an application point of view, you really, really care where your data flows in your application. So if you have a good solution for this, you're golden. Lots of people are going to care. Okay, so luckily, if you go surveying the literature, it turns out taint tracking is a well-studied problem. You get like at least 45,000 hits. Unfortunately, 45,000 hits. But that doesn't necessarily mean that it's a solved problem, because if you start narrowing your search from the latest literature in the area, people are still publishing in this space and they're still working in this space, because it turns out that if you actually want to deploy this on industry software at scale and make this work for real in practice, it's not a solved problem. There's a lot of issues you run into. You still get a lot of hits, even if you look for recent work. So of course, we decided to add to the Google Scholar amount of papers on taint tracking ourselves. So we motivated based on the problem I just described. We implemented our own Java taint tracking tool. And the idea here is that we implemented a compositional analysis where you analyze each component in isolation. In this case, each component is a procedure. And then you combine them, you go bottom up and combine them until you get a comprehensive view of how your application behaves. And the idea here is that because you're compositional, you can scale. We tried the other version, the whole program thing, and it doesn't work that well. Another requirement for us on this analysis was that if you're doing taint tracking and you want to, again, deploy it in industry, it really has to be precise. There's not many corners you can cut when you're looking at like real code out there, especially object-oriented code. So your analysis has to be flow, object, field, and context sensitive. You're not allowed to have abstractions that merge the effects of one method in different calling contexts, especially in Java. And finally, because again, we really care about things being correct, we implemented, well, we came up with a sound algorithm because there's always gap in implementation and theory. And our algorithm is sound under some reasonable assumptions. So things like maybe, if you have reflection, all bets are off. We don't handle reflection. So we're done, right? Well, no, not at all. It turns out that there's quite a gap between kind of solving the research problem of precisely tracking tainted data, or not even solving, contributing to working on this problem. So there's a big gap between like the research question and actually deploying this in practice. So that's what I'm going to talk a bit about next. So one of the things is that when you look at code in the wild, programming language is never just a programming language. It's actually a whole ecosystem. So for Java's concrete example, there is a long tail of libraries and frameworks. And you may say something like, remember our assumption, right? We don't support reflection, so if you're using reflection in your code, you deserve all the vulnerabilities that are coming to you, right? Well, the problem is that reflection, well, most developers, thank God, don't write reflection for the fun of it. It comes up in all of these libraries and frameworks that do really crazy things with it. And if you don't have custom support for it or any understanding of that, you're not even going to be able to build a call graph or find an entry point to your application. So the research problem here that I think is both interesting and very challenging is, can you automate supporting new libraries and frameworks for a new language? Writing them all by hand is very tedious and error-prone, a long process. And I know there's some work in this area trying to look at dynamic analysis, but I don't know of anything that actually kind of, you can actually kind of, solves the problem fully. So that's one problem, that programming languages are not programming languages, they're big ecosystems. Another one is that it's actually, when you look at industrial software, it's actually never just one programming language. You probably have some microservice in Java, but you're going to have another one that's in Python, maybe Golang, maybe JavaScript. And this is obviously not a problem just for cloud applications, it's a problem for any kind of real big application. So the question here is, can you build an analysis that can reason compositionally about different programming languages? And how do you scale it so you don't spend like 3 years implementing a new analysis for each programming language? And at this point you may say, well, do you have to reason about them together? Can't you just like do some kind of compositional proof by contract type thing? Well, the problem is that when you are looking at these things like this kind of data flow security properties, they're very non-local. So what usually happens is you have your source of untrusted network data or maybe customer data is somewhere in one point, in this case, that the upload API gate point service, and the sync is in the different microservice, and your validation is happening somewhere else in the middle. So if you're just going to look at one of these lambdas in isolation and assume all the inputs to it are untrusted or sensitive, you'd have like a lot of false positives, and that's not great. So the challenge here is you have to be able to handle multiple programming languages and the different frameworks. Okay, but we're not done. There's still more things you need to handle. So just reasoning about code is not enough. Because when you have these cloud resources, there are a bunch of implicit flows between them, depending on how you configure them. And let me explain that with a concrete example. So here I have this nice little edge that says trigger from the thumbnail store to the thumbnail service. And turns out the way you can implement this is you can add, you can configure your S3 bucket with a Lambda trigger. And you can do it programmatically, or you can go around clicking in a console, and you can say, okay, I'm going to add a trigger. So whenever this little S3 bucket here gets any kind of create object event, then call my Lambda function automatically. And what the Lambda function call is going to look like, it's going to have a handler that takes an S3 event, and it can get the bucket name, the source key, it can get the actual object that got updated. So the idea here is you have all of these implicit flows that where code is not enough. You need to understand the resource configuration behind the code. Okay, one more. So in addition to these implicit flows, some of the services actually use domain-specific languages to express certain types of computations they can do. And one such example is what we call step functions. So step functions are actually this really cool feature. It's a workflow orchestration framework that lets you define basically a finite state machine between your Lambda functions. And you can say things, you can sequence them, you can have choice operators, you can have parallel computation, you can branch your workflow, you can have joins, you can have error handling. So lots of interesting things. And the way you create these state machines is with Amazon State Language. It's unfortunately a JSON format, but there is a spec online you can read and make sense of it. And then there's, you can use JSON path, basically lets you project the inputs and outputs of the various task nodes. So if anybody here is looking for a thesis topic, please implement a static analysis for this. I think it's actually kind of low-hanging fruit, and it's really, I think it's a really cool problem. And so I was talking about challenges that didn't go away, but I still want to claim that it's still easier to do this in the cloud. Because even if you have all of these programming languages, you have some domain-specific languages, you still have these implicit flows, the good news is that you can always get like the ground truth of the architectural model of the application you're building. And because it's all programmatic, you can do what is called describe calls, and you can say, give me all the Lambda nodes in your application. You can iterate over them. You can get the code that is deployed. You can get all of the finite state machines I was talking about. This is what this API does here. And you can do a describe call and get what definition of the state machine is, and then you can build your own analysis there. So yeah, because it's in the cloud, you can at least get the ground truth of how these things fit together. Okay, so to conclude, verifying industrial software is hard. It's a bit easier in the cloud, but it's still not, it's not a walk in the park. There's still lots of work to be done. So the reason it's easier, it's because you have these computer readable contracts, you have these describe calls. There are domain-specific languages, but they're uniform. Those step functions, yeah, it may look a bit gnarly, but a lot of people are using it. So you implement analysis for that, a lot of people are gonna be happy with you. But challenges still remain. One big problem is there's multiple programming languages, and I haven't found a good way to make everyone use the same programming language, like Haskell or something. There's a lot of frameworks out there, and those can really change the semantics of the application. So if you don't support them, you're not gonna be able to analyze them. There's implicit flows in the resources. So while you can get the information for them, you still have to support them in your analysis. And there are still domain-specific languages that require their own custom reasoning for them. And finally, before I conclude, I just want to talk about two challenges I haven't mentioned at all before. But these were two, what I think were interesting aspects that, things that I didn't see coming when I came from academia to industry. One of them is, may sound kind of obvious, but how do you quantify the coverage of your analysis, and how do you communicate that to stakeholders? As an example, we said, we have a taint analysis, it's sound. I can kind of explain what sound means to people that are reasonably technical, but not formal methods people. But then they come back with a question. It's like, okay, fine, but like, how bad is it for my application? What are you gonna miss? And the problem with soundness and false negatives is you don't know what you're going to miss. So can you have any ways of actually knowing where your analysis goes off the rails or where it has blind spots? So you can provide, at the very least, you can provide some human readable thing that is like, okay, we were able to analyze this with high confidence, but this bit here, I don't know what's happening here. Maybe you need a security engineer to look at it. Or any other ways of quantifying the coverage and the impact of your analysis. The second point is basically stability of analysis. So the thing about any industrial software that anybody cares about is that it doesn't stay the same. It constantly keeps changing, and there's more features added, it's bug fixes, everything. So you can't be in a situation where somebody changes 3 lines of code of their application, and suddenly your static analysis results go off the rails, or your proofs stop failing, whereas before they were succeeding. And this is something that actually kind of came to bite us when we tried to integrate proof into the CI/CD. Because there would be like a small innocuous change. Most of the times you could repair the proofs easily, but sometimes it would just mess up with a heuristic of the backend SMT solver, and now it suddenly times out. And an even worse situation is when you haven't updated the system under analysis, but you upgraded your solver. It's overall way better than what was before, but for this one specific thing, now it times out, and people are blocked from deploying their things. So this is, again, I think a very interesting space where can you design some of this automation, some of these tools in a way that makes sure that they're not sensitive to small changes in the input of the analysis? And a potential solution here is counterintuitively actually maybe go more manual, have more manual specification, because if you, well, to a certain extent. Anyway, but yeah, I think we don't have a solution, we just have a problem there and some ideas. Okay, so with that, I think I'm gonna stop here and take any questions you guys may have. Thanks.
So I guess that all this is implemented, right?
Oh, some of it is implemented. We're working on internal tools for it, and I meant.
Okay, that was not my question. My question is, in practice, my question was about incremental verification.
Yeah.
If you do a small change, and you now have to verify again, what do you do in practice? You run from scratch, or do you try to use information from the previous rounds? It's a general question in verification, and since this seems practical, yes.
Yeah, well, I can talk from the static analysis point of view because we've actually worked on that. Yeah, we try to actually, in this kind of compositional approach, if we've actually tried to, enables you to implement an incremental analysis so that, say, a method changes, you only reanalyze that method and the callers of that method. So you don't have to reanalyze the whole application again. You will probably have to throw away your call graph and rebuild it from scratch. And this can result in really huge savings. Like we did an experiment where we were basically comparing analyzing everything from scratch versus analyzing just things that were changed in a Git commit, like looking at a history of some repositories we cared about. Yeah, that worked really well. I think it ended up being 10% of the original time, and that was without any optimizations. Yeah. Yeah.
Okay. No, thank you.
Hey, thank you. Really interesting talk. Could you speak a little more on the specification of the sort of what you call like low-hanging fruit thesis problem? I didn't think this would be my thesis, but I'm very curious about it.
Well, I don't know if I'm an expert on collecting low-hanging fruit thesis problems, but I will say I think a good way to find impactful problems, not necessarily low-hanging. But actually, I think if you pick a
Oh, I meant the one that you talked about, like in this talk. Yeah, yeah, the one that you said, oh, like this, if someone wants to do as a thesis, like implement the static analysis for this.
Oh, for that one specifically?
Yeah, could you speak a little more on that?
Yeah, I mean, there's basically a domain-specific language that defines state machines that combine how lambdas interact with each other. And I'm pretty sure it's Turing complete. And you can try to build a static analyzer for it that tries to figure out how the data flows through these different, when you combine different lambdas in a step function. And you can, okay, the reason I think it's easier than just going off and implementing some static analysis for JavaScript or something is because there's, I think when you're looking just at the state machine language, you can get away without reasoning about aliasing and some other hairy things. Because the language itself is relatively simple, but I guess you'll have a big impact in compared to just analyzing the code. If you analyze the state machine language and combine it with the code analysis, you can get a lot of interesting results. Did that answer your question? I'm not sure.
Yep, thank you.
Oh, no, I mean, there is definitely a problem of that. This is not something I've worked on directly, but I think a common thing that comes up is, other people have worked on this, is maybe you have some kind of distributed protocol you want to verify, and you have your handwritten description of the protocol, and you verified it in your favorite interacting theorem prover, or like, and then the question is, what's the connection between that and the actual implementation? And I think an easy error to make here is kind of like, well, there's no way I'm going to be able to verify the whole end-to-end system in the wild, so I'm just going to throw my hands in the air. But I think there are incremental steps you can do, and there are kind of degrees of assurance. I mean, sound is sound, but there are degrees of assurance you can get. So actually, just by looking at the protocol, there is a huge value in that. Historically, people have found bugs in protocols by trying to verify them, but also it enables the developers to actually understand it a lot better and how it works. And then the other aspect is based on what the formal description of the protocol is, you can start generating monitoring or runtime assertions that check if you're violating the protocol. And other work you can do that we had one of our sister team do, which was you can have like a reference implementation that is a lot simpler and that you can actually formally verify it. And then you have, again, some kind of monitoring by running it alongside with the real implementation and kind of check that they're going in sync. So yes, there is a huge gap, but don't let that discourage you. There are like incremental steps you can do to kind of keep moving in the right direction and kind of keep building assurance. Yeah.
Thank you very much for the talk. I wonder, like, how much effort do Amazon Web Service or Amazon as a whole put into formal verification of their platform, or like how big is the verification team in the company? If you may answer.
Yeah, well, I'm pretty sure I'm not allowed to say headcounts, but I mean, okay, how big? And, okay, as a concrete example, we have an internal Amazon conference for the formal methods community. So it's big enough that we have our own workshop that meets once a year, and it would more than fill this room. And these are people who work in the space, but also people who use the tools and care about it. But a lot of people work in the space. Yeah, there's a lot of interest in this area, and something I didn't even mention at all. I'm sure you guys have heard about LLMs and hallucinating, and I think there's also like a lot of interest in whether, just in general in the area, about whether you can use automated reasoning to reel this in and actually get trusted results out of them. So there's a lot of, yeah, we care a lot about it, and thank you for reminding me. We're hiring interns, so if anybody wants internships, please come talk to me. Not just my team. If you don't like static analysis, there's other teams that do different things. Tell me what your interests are, and I can put you in touch with somebody. But yeah. Mm. Yeah, I feel like what I found works best. It's maybe unfortunate. Oh, no, not unfortunate, but it's kind of like show results. There is this notion, and it's not just Amazon specific. It's I think a software engineering notion about like building the minimum lovable product. So as an example, if you can look it up online. There's like this the skateboard philosophy of building software engineering. You can look it up. There's a cool comic. Basically, the idea is if you build a prototype quickly that shows results and pick your and then they're gonna start believing you that it can actually work. So try to find like a narrow problem that you can solve really well, and then show them it works. And if they're like, well, that's the scale. I've tried to use formal methods in the past. It was a mess. Should I do it? And you're like, well, no. We used it on this little thing, and it worked, and we found something, or we proved that there couldn't be anything that go wrong. So I would say kind of start small, targeted, and keep showing results that it works, and then people are gonna trust you. And they want metrics a lot of the time, but I can't give you metrics about false negatives very easily. That's a hard one. There's like ground truth sometimes, like there's label data sets for like, benchmarks. We know they have vulnerabilities. Did your tool find them? But that's not real because they're biased. So it's like a whole complicated mess. But yeah, I'm not sure if that answered the question. It was a bit of a side.